Hello, I'm Andrew Lobb. I'm a mathematician at Durham University, and this podcast is going to be about volumes of revolution. The first question to ask about volumes of revolution is, what's the point? And what's the point is a question that one's allowed to ask at university. So the point of volumes of revolution is really to showcase another application of integral calculus. So integral calculus is very useful for finding the area under a curve. Turns out you can also use it to find the volume of a solid. Now, since we're just using one integral to find the volume of a solid, there better be pretty strong dependence of that solid on a single axis in three-dimensional space. That's why we consider volumes of revolution as opposed to random objects, volumes of random objects, because volumes of revolution, to form them you take a two-dimensional shape and rotate it around the axis, so there's strong dependence upon that shape of the axis of rotation. Okay, so how do we approach the topic of volumes of revolution? How are we going to compute these things? Well, there's the approach you use at A level, and it's the same approach you use to answer any of your questions at A level, which is you remember a bunch of formulae and then you learn how to apply them in certain situations. Now, at university, we tend not to like formulae as much as we like ideas. And I'll let you into a little secret. Ideas are a lot easier to remember than formulae. And so these ideas that we remember often are pictorial. So I'm going to show you a couple of pictures, and they'll be familiar to you, I hope. And we'll talk through them, and then we'll apply these pictures to the topic of volumes of revolution. Okay, so let's take a look at this first slide. It's quite a busy diagram. What we have here is a graph, y equals f of x, some function of x. And I'm interested in finding the area under the graph between the points A and B. So the first thing I do is make an approximation to this area. This is something that should be familiar to you from your studies of integration. So what I do is I take the interval a to b and divide it up into n equal subintervals, each of length delta x. So delta x is therefore b minus a divided by n. And then if I want to figure out the area under these rectangles, I have a formula for that that's obviously true, and this is the nth Riemann sum. So then that's an approximation to the area under the graph. As I increase the value of n, these rectangles are going to get thinner and thinner, and the approximation is going to be better and better to give me the actual area under the graph in the limit as n goes to infinity. So that's what's written in the bottom right. The area under the graph, which is this integral from a to b of f of x dx, is equal to the limit as n goes to infinity of this nth Riemann sum. Okay, so that should be familiar from integral calculus, and that's the first picture that we're going to bear in mind while we try and figure out how to approach the problem of computing volumes of revolution. Second picture is now being displayed, and here we show the volume of three very simple shapes. I've called them the disk, the washer, and the cylinder. So what these shapes have in common is they're all rotationally symmetric, and they all possess a small amount of thickness. In these diagrams I've called the thickness epsilon. That's a typical letter we use at university to mean something small. So the disk has a volume that depends just upon its radius and the thickness, and of course it's the area of the cross-section times the height. So that's just pi r squared times epsilon. The washer, so you can think of the washer as being a disk of radius big R, and then you've drilled out a smaller disk of radius little r. So I can figure out the volume of the washer by subtracting the volume of the little disk from the volume of the big disk. So the volume works out to be this formula, pi times big R squared minus little r squared times epsilon. Lastly, a cylinder. So the cylinder has radius r, has height h, and then it's been thickened up a little bit to be epsilon. So in this case, I'm not giving a precise formula for the volume. I'm giving a sort of approximation to the volume, a good approximation to the volume, when epsilon is small. And how do we compute it? Well, first part of that formula is 2 pi r. That's the circumference of the circle with radius r. And then I multiply that by epsilon, so that thickens it up, and that gives me the area of the cross-section of the cylinder, at least to an approximation. And then I multiply the area of the cross-section by the height h, giving me that complete formula, 2 pi r times epsilon times h. So these are the ideas that we're going to keep in mind while we tackle the problem of computing volumes of revolution. So we learn mathematics by doing it or by seeing it done. So I'm going to present 2 examples where we use these ideas to compute volumes of revolution of a particular solid. Okay? It's going to be the same solid each time, but we're going to use different methods. All right, so how am I going to form this solid? Well, to form a volume of revolution, you're meant to take a region, an area, and then rotate it around an axis. So my axis is up on the board. It's this blue line, x equals minus 2. I'm going to rotate around this. And the area that I'm going to rotate is this area here between these 2 curves. So one of the curves is y equals x cubed plus 1, and the other curve is y equals x plus 1. The region I'm going to rotate is this region. Okay. So let's add a few decorations to our graph, figure out some intercepts. So this is 0, this will be 1, 1, and they intersect at 1, 2. So the idea is going to be the following. First of all, we're going to write down, so the idea is really that we're not going to use a formula, which would be tempting. We're going to write down an approximation, and then we're going to think about the limit of the approximation to give us an integral that's going to give the exact volume. Okay, so how's the approximation going to work? The approximation is going to work by dividing this area up into thin rectangles and then rotating the thin rectangles around the line x equals minus 2, figuring out that the volumes that they produce, adding them up, and that's going to give us like a Riemann sum. And we're going to take the limit of these Riemann sums as we put more and more rectangles into the area. So first of all, we've got a choice to make. Do we want to chop this region up vertically or horizontally? It's always going to make sense to chop either parallel to or perpendicular to the axis about which you're rotating. And in this situation, it's not going to matter to us which direction we choose. Some situations it will, but you'll learn these yourself by trial and error. So we could choose vertically or horizontally, and in fact we're going to do both. But let's start with vertical slicing. So the idea is I'm going to take this region and slice it up into rectangles like this, or approximate rectangles. And then each rectangle is going to be rotated around the line x equals minus 2, and it's going to give me a solid whose volume I know already. So these are thin rectangles, and when I rotate them around the line x equals minus 2, what am I going to get? I'm going to get nothing but a cylinder. So if we look back at the sheet, you can see our formula for volume of a cylinder, which is 2 pi r times epsilon h. Let's identify these things. In particular, let's identify epsilon. So what we're really doing when we're chopping up this region into thin vertical rectangles is we're chopping up this interval from 0 to 1. And we're chopping it into n-equal pieces, and the length of each piece is going to be delta x, and delta x, of course, therefore has to be b minus a over n. In our case, b is 1 and a is 0, so this is just 1 over n. So in our formula we'd have epsilon equals delta x, and also in the formula for the volume of a cylinder, two other quantities. Delta x is the thickness. We also need to take care of the height and of the radius. So the height and the radius both just depend on where we are in this interval 0, 1. They both depend on xi. So the radius is a function of xi, and the height is also a function of xi. So if we're going to write down an approximation, we've got to add up volumes of n of these cylinders, and volumes of the cylinders are like this. That's the circumference, and then I thicken this up by epsilon, it's delta x, and then I multiply by the height. And of course, just as in our first picture that we're bearing in mind, as we increase the number of cylinders, as we let n tend to infinity, this approximation gets better and better. And this thing has the form of a Riemann sum, where the function, the f of xi, if you like, is just this 2 pi rxi times hxi. So in the limit, we get the actual volume, and we can determine the actual volume by an integral. So we take the limit as n goes to infinity, and what happens is we get the integral over the n points of the interval that we were chopping up, at 0 to 1, and 2 pi r is now a function of x, and h is a function of x, and the delta x is replaced by this dx. So all we need to do now to determine the integral is to figure out what r is in terms of x and what h is in terms of x. So let's think about that. So r of x is what? Well, if x is here, the radius is from this line that we're rotating around up to here, and that distance is 2 to get to the y-axis, and then x to get to x. So the radius is just 2 plus x. And what about the height? So at a point x, the height is the distance between these two curves. So the curve on top is y equals x plus 1. The curve on the bottom is y equals x cubed plus 1. So we've got to subtract those two quantities from each other in order to get the height. So x plus 1 is on the top, and x cubed plus 1 is on the bottom, giving us that the height is x minus x cubed. And then we can take these formulas and substitute them into our integral, and then we've just got an integral of a polynomial function of x, and that's something that's easy to compute, so I'm not going to do it for you. In a second, we'll get another integral where instead of chopping this region up into vertical rectangles, we chop it into horizontal rectangles.